This video is on rotational kinematics. Question 1. Define, state the equation, and give the units of angular position theta. Angular position is the location of an object in a circle. So S is equal to r theta, where S is linear distance, r is a distance from the center of the radius, has units of meters, theta is in radians, and we know 360 degrees equals 2 pi radians. So take a look at this picture. What's the distance around a circle? That's called the perimeter of a circle, or a circumference. The circumference. That's 2 pi r. So take a look at this yellow equation. If you let theta equal 2 pi, you have 2 pi r on the right side and the distance around the circle S on the left side. So this equation makes sense if you believe S is equal, if you believe that the circumference is equal to 2 pi r. So once again, theta is circular or angular distance, position, and S is, I apologize, R is in meters on the right side, S is in meters on the left side. So theta is position, which has units of radians, which is not a real unit. So we could always just ignore it. Question 2. Define, state the equation, and give the units of angular speed omega. The terms angular speed and angular velocity are used interchangeably. The following equation relates linear speed, v, with angular speed omega. V equals r omega. So v on the left-hand side is linear motion, omega on the right-hand side is angular motion. Omega has the units of radians over second. Because the left hand has units of meters, so the left hand has the units of meters over second, so the right hand has to have the units of meters over second. R is in meters, omega is 1 over second. So when we're going in a circle, that circular speed, angular speed, is omega, and tangent to the point is v, velocity. Question 3. Define, state the equation, and give the units of angular acceleration A. In linear motion, acceleration is when an object speeds up, slows down, or changes direction. A is equal to dv over dt. In circular motion, angular acceleration is a change in angular speed over time. So alpha is angular acceleration, has units of 1 over second squared. So this equation relates linear acceleration with angular acceleration. A equals r alpha. So A is linear, meters over second squared. The right is circular or angular, which is meters over second squared. R is seconds, R is in meters, alpha is in 1 over second squared. So the units on the left-hand side is equal to the units on the right-hand side. So radial acceleration is towards the middle, tangential acceleration is 90 degrees, and acceleration total, you could see it's when you sum up the two. Question 4. Convert the Suvat equations from linear motion to circular motion. First, let's remember 360 degrees is 2 pi radians. Here, these three highlighted, the left-hand side is linear, position, velocity, and acceleration. The right-hand side is angular, position, velocity, and acceleration. Omega equals 2 pi f, where omega is the linear speed, or omega is angular speed, f is frequency, the time it takes to complete one revolution. Okay. Now these four equations have translated linear equations to circular equations. So you can see there is a arrow here. So on the left-hand side is linear equations, on the right-hand side is circular motion equations, or angular motion equations. Angular and circular both pretty much mean the same thing. Okay. Question 1, that's a mistake. This was question 1, 2, 3, 4. This is question 5. Convert the following to SI units. So we know this is equal to the number 1. So I just converted degrees to radians. Here I converted 1 over seconds to radians over seconds. This is radians over second. 15 degrees per hour, we want this to be in radians per second. So the numerator is equal to the denominator in this parentheses that's been highlighted. The numerator is equal to the denominator in this parentheses that's been highlighted. And finally, the numerator is equal to the denominator in this parentheses highlighted. Let's convert revolutions per minute over hour to radians per second squared. So these 3 fractions that I highlighted, each one is equal to the number 1. Because the numerator, for example, 1 hour is equal to the denominator, which is 3,600 seconds. The numerator, 1 minute, is equal to the denominator, which is 60 seconds. And the numerator, 2 pi radians, is equal to the denominator, 1 revolution. Okay. A helicopter prop accelerates from 800 revolutions per minute to 2,000 revolutions per minute in 5 minutes. Part A, calculate the average rotational frequency in revolutions per minute. Part B, calculate the total rotations executed. Part C, Casey Potter's wheel accelerates from 45 over seconds to 75 over seconds over an angular displacement of 72 radians. Find its angular acceleration. So we're going to use this equation. Question 4. A saw blade whose initial velocity is 4 over seconds accelerates at 2 over seconds squared. During this interval, the blade rotates 165 radians. Find the time of this interval. So this first highlighted equation is a Suvat equation. This is the angular motion equation. Then solve for time. Question 5. We're given this. Also, we're given this boundary condition, this initial condition. Part A, find equations for alpha and theta. So if you want alpha, we take the derivative of omega, d omega over dt, to get this. If we're given angular speed and we want to find angular position, we have to integrate. So we have this equation here. So we get this value here. Now at t equals 1, we know theta equals 36. So now c is equal to 12. So with this equation, we could just plug in the constant c equals 12. Part B. At t equals 4, calculate the values of theta, omega, and alpha. So now we have equations for theta, omega, and alpha. So just plug in the value t equals 4 for these 3 equations. Part C, calculate the average angular speed for the interval t equals 1 to t equals 4. Part D, calculate the average acceleration for t equals 1 to t equals 4. Next question. The Earth spins on its axis once every 24 hours and orbits the Sun once every 365.25 days. Looking down on the solar system, the Earth both spins on its axis and orbits the Sun counterclockwise. Finally, the spin axis of the Earth is tilted 23.5 degrees from the plane of its orbit. Part A, calculate the angular speed of the Earth's spin omega sub s. Part B, calculate the angular speed of the Earth's orbit, omega sub 0. Part C, calculate the ratio. Part D, calculate the magnitude of the total angular velocity of the Earth's motion. Next question. The equatorial radius of the Earth is 3963 miles, where 1 mile equals 5280 feet. Okay, you could read the rest. The length is 1 minute, and we're going to convert 1 minute to feet. Question 8. The blade of Vahid's power saw, whose radius is 3 meters, takes 0.26667 seconds to slow from angular speed 32 over seconds to rest. Part A, calculate its angular acceleration alpha. So we're going to use the equation delta W over delta T. Part B, calculate its tangential acceleration. V equals R omega. And A tangential is V squared over R. We look at the blade 0.6667 before it stops. Calculate its angular speed omega. So if it stops in 0.26667 seconds, 0.6667 seconds before it stops, that means it's already been rotating for 0.2 seconds. Part B, calculate its tangential speed V. V equals R omega. Part E, calculate its radial acceleration A radial. Is V squared over R. Part F, calculate its total acceleration A total. Part G, calculate phi of A total. Part H, this is important, so you have a conceptual understanding of what's going on. Sketch A tangential, A radial, A total, and phi. The blade was spinning counterclockwise. Part 9. Two wheels connected by recording tape are spinning as shown below. And we're given the radius of A, the radius of B, that should be B, and the frequency of B, R sub B. Part A, calculate the frequency of the smaller wheel in revolutions per minute. So V sub A equals V sub B. And V equals R omega. And omega equals 2 pi F. Part B, calculate the speed of the tape in the rim of each wheel. So V equals R omega.